In 1939, eccentric billionaire and aviation pioneer Howard Hughes summoned senior executives from the Lockheed Aircraft Corporation to a highly classified meeting with a demand that seemed technically impossible for commercial aviation at the time. Hughes, who held a controlling interest in transcontinental and Western air, wanted an airliner capable of flying 44 passengers coast to coast across the United States non-stop, cruising comfortably at nearly 300 miles per hour. This speed requirement was astonishing, as it meant a massive commercial transport would fly faster than many frontline military fighter aircraft of that era, completely disrupting the established timelines of domestic travel. This ambitious mandate fundamentally birthed the Lockheed Constellation, an aircraft that achieved its legendary performance through a bizarrely curved fuselage shape that swooped like a dolphin, and a distinctive triple-tail design that was not originally born of advanced aerodynamic theory. Instead, that iconic three-finned tail was strictly dictated by the ceiling height of existing airline maintenance hangars, forcing engineers to split a single massive vertical stabilizer into 3 smaller ones, simply so the aircraft could fit indoors for routine repairs. At the dawn of the 1940s, commercial aviation was a grueling low-altitude endurance test dictated by weather systems and terrain, rather than passenger comfort or rapid schedules. The industry standard was the Douglas DC-3, an undeniably revolutionary machine, but one that was unpressurized, relatively slow, and required multiple stops to cross the North American continent, exposing passengers to punishing turbulence and deafening noise. Boeing had attempted to solve the long-haul problem with their Boeing 314 flying boats, but these maritime aircraft were aerodynamically inefficient, incredibly expensive to operate, and restricted to coastal cities with large bodies of water. Transcontinental and Western air needed an aircraft that could climb high above the thunderstorms, cross the Rocky Mountains with ease, and deliver passengers from New York to Los Angeles without the agonizing series of layovers. Hughes mandated absolute secrecy during the development phase, expressly forbidding Lockheed from selling the design to competing carriers like American Airlines or United Airlines for the first few years of production. This corporate exclusivity was intended to give transcontinental and Western air an insurmountable monopoly on premium, high-speed, high-altitude travel, shifting the commercial focus from short, regional hops to transcontinental point-to-point dominance. The core engineering challenge was creating an airframe that was large enough to hold dozens of paying passengers and their luggage, yet streamlined enough to minimize drag at unprecedented cruising speeds. Lockheed engineers chose to completely pressurize the cabin, a relatively new concept that required the fuselage to act as a pressure vessel, maintaining a safe, breathable atmosphere at 20,000 feet, while the outside air was freezing and thin. If detailed technical breakdowns of aviation design and airline strategy interest you, subscribe. I have got more of these coming. To achieve this pressurization without suffering catastrophic structural failure, a cylindrical shape is structurally ideal, as it distributes outward pressure evenly across the metallic skin, preventing fatigue points from concentrating in sharp corners. However, a purely cylindrical tube presents a massive aerodynamic problem when attached to the wing, as it tends to alter the airflow distribution and disrupt the center of gravity as the payload changes. To solve this aerodynamic dilemma while maintaining the structural integrity of a pressurized tube, Lockheed Chief Engineer Clarence Kelly Johnson and his team designed the famous cambered fuselage, which gives the Constellation its distinctive, drooping nose and upward swooping tail. This continuous curve is actually an airfoil shape in itself, designed to generate a small amount of aerodynamic lift, which relieved some of the lifting burden from the main wings and reduced overall drag. More importantly, this sweeping curve allowed the wing to be mounted centrally to reduce interference drag, while simultaneously keeping the passenger cabin floor completely level during the nose-down cruising attitude. The front gear could be kept relatively short, saving crucial weight, while the upward sweep of the rear fuselage kept the tail high enough off the ground to prevent devastating tail strikes during rotation on takeoff. But this elegant solution introduced a heavy manufacturing penalty, as nearly every single aluminum frame and stringer in the fuselage had to be a unique, custom dimension, completely eliminating the cost-saving benefits of constant section manufacturing used by their rivals. For the wing design, Lockheed relied heavily on their military experience, making a decision that was both brilliant and highly consequential for the operational life of the new airliner. Instead of designing a completely new wing from scratch, the engineering team effectively took the highly successful low-drag wing profile of their Lockheed P-38 Lightning interceptor and scaled it up to massive proportions. This gave the Constellation a high aspect ratio wing, meaning it was very long and narrow, which is incredibly efficient for high-altitude, long-distance cruising, significantly reducing lift-induced drag compared to the stubbier wings of previous airliners. To compensate for the high stalling speeds that naturally plague such narrow high-speed wings, Lockheed fitted enormous Fowler flaps that rolled out and extended backward on complex steel tracks. When fully deployed, these Fowler flaps dramatically increased the total surface area of the wing and altered its camber, allowing the massive airliner to fly slowly enough to land safely on the relatively short municipal runways of the era. However, scaling up a fighter wing to the size of a heavy transcontinental airliner created an immediate and dangerous problem regarding the sheer physical force required to move the control surfaces. At cruising speeds approaching 350 miles per hour, the aerodynamic pressure pushing against the massive ailerons and elevators was far too immense for a human pilot to overcome, using traditional steel cables and pulleys. To solve this, Lockheed was forced to implement one of the very first hydraulic boost control systems in commercial aviation, essentially equipping the aircraft with power steering similar to what you would find in a modern heavy automobile. While this system allowed pilots to maneuver the enormous aircraft with relative ease and precision, it introduced miles of pressurized hydraulic fluid lines, pumps, and valves, adding a tremendous layer of mechanical complexity and vulnerability. If a hydraulic seal failed or a pump shattered mid-flight, the pilots had to rely on a manual reversion system, fighting against horrific control stiffness that required immense upper body strength just to keep the aircraft flying straight and level. The propulsion system chosen to drag this massive, pressurized aluminum structure through the stratosphere was the formidable Wright R3350 duplex Cyclone engine, a mechanical marvel that became the heart and the Achilles heel of the Constellation. Each of these engines was a massive 18-cylinder air-cooled radial, displacing 3,350 cubic inches, and capable of producing over 2,200 horsepower at takeoff. Generating that much power required burning vast quantities of high-octane aviation gasoline, which in turn produced a staggering amount of internal heat that had to be dissipated quickly to prevent the engine from literally melting itself apart. Because these were air-cooled engines, they relied entirely on the forward speed of the aircraft, forcing freezing high-altitude air through a tightly cowled engine nacelle, flowing over precisely designed metal cooling fins attached to each of the 18 steel and aluminum cylinders. The engineering necessity of keeping the aerodynamic drag low meant the engine cowlings were incredibly tight, leaving very little margin for error when it came to managing internal engine temperatures during high-power operations like a heavily loaded takeoff. This tight cowling design created a relentless battle between aerodynamic efficiency and thermal reality, a nested loop of engineering compromises that plagued airline maintenance crews throughout the lifespan of the aircraft. To regulate the airflow and temperature, the engines were equipped with large adjustable metal cowl flaps at the rear of the nacelle, which the flight engineer could open wide during steep climbs to maximize cooling air, and close tightly during cruise to eliminate excess drag. However, the rear row of the 9 cylinders constantly suffered from poor airflow, as the front row effectively blocked the incoming wind, causing the rear cylinders to run dangerously hot, especially during long summer departures from high-altitude airports. This extreme thermal stress routinely caused the magnesium crankcases to crack under pressure, leading to catastrophic oil leaks that, when ignited by the glowing exhaust stacks, resulted in terrifying and violently destructive engine fires. The fires were so notoriously common during the early years of operation that airline crews sardonically referred to the Constellation as the finest three-engine airliner crossing the Atlantic Ocean. Knowing what you now know about its operating costs and compromises, do you think the design approach was worth it for the airlines? Share your thoughts below. To truly understand the operational reality of this aircraft, one must look past the glossy, romanticized airline posters featuring glamorous movie stars sipping champagne and examine the grim, oil-soaked reality of the maintenance ramp. Every single engine required dozens of gallons of thick lubricating oil to function, and it was considered perfectly normal for the massive radial engines to consume several gallons of oil per hour during a routine transcontinental flight. This immense oil consumption meant that turnaround times at airport gates were incredibly labor-intensive, with mechanics dragging heavy hoses and ladders to manually replenish the massive oil tanks housed within the engine nacelles while the exhaust pipes were still blistering hot. Furthermore, the high-octane aviation fuel heavily relied upon tetraethyl lead to prevent engine knocking under high pressure. But this lead formulation created a secondary nightmare for the ground crews tasked with keeping the aircraft flying on schedule. The lead would rapidly accumulate and foul the enormous spark plugs, 2 for each cylinder, totaling 144 spark plugs across the 4 engines, requiring mechanics to meticulously remove, clean, and replace them after nearly every single long-haul journey. When contrasting the Lockheed Constellation with its primary commercial rival, the Douglas DC-4, and its pressurized successor, the Douglas DC-6, the raw economic realities of post-war commercial aviation become brutally apparent. The Douglas aircraft were visually conservative, featuring straightforward cylindrical fuselages and conventional single-tail designs that lacked the sweeping, artistic grace of the Lockheed airframe, but they were vastly cheaper to manufacture and far easier to maintain. Douglas engineers prioritized accessibility, ensuring that engine components, hydraulic lines, and electrical systems were easily reachable by mechanics standing on standard ladders, dramatically reducing the labor hours required for routine inspections and parts replacement. In contrast, the Constellation was a tightly packed, highly integrated machine, where accessing a simple hydraulic valve might require dismantling several adjacent systems, keeping the aircraft stuck inside the hangar while the rival Douglas machines were out generating revenue. Airlines quickly realized that while the Constellation sold tickets based on its speed and undeniable curb appeal, the Douglas DC-6 was the reliable, predictable workhorse that reliably printed money for the shareholders week after week. Despite the maintenance headaches, the passenger experience aboard the early Lockheed Constellations was heavily marketed as the absolute pinnacle of mid-century airborne luxury, representing a massive leap forward from the unpressurized horrors of the pre-war era. Passengers who could afford the exorbitant ticket prices were treated to plush, thickly upholstered seating, lavish hot meals prepared in a fully equipped onboard galley, and an overall aesthetic that aimed to mimic the finest Pullman train cars. Because the aircraft was fully pressurized, it could ascend above the most violent, stomach-churning weather systems that plagued lower altitudes, offering a significantly smoother ride that drastically reduced the widespread instances of debilitating air sickness. However, the term luxury is highly subjective when placed in the context of large, reciprocating piston engines, as the noise inside the cabin was still a dominating, inescapable physical presence that permeated every single phase of the flight. The massive propellers, spinning at hundreds of revolutions per minute just a few feet away from the thin aluminum fuselage, generated a low-frequency drumming vibration that easily penetrated the heavy layers of fiberglass soundproofing blankets hidden behind the cabin walls. For passengers seated in the forward section, precisely in line with the propeller arcs, the deafening roar and relentless shaking made normal conversation completely impossible, forcing them to shout over the mechanical din for hours on end. Airlines attempted to mitigate this by placing the most expensive, premium seating at the very rear of the aircraft, far away from the engines, but the long, flexible fuselage had a tendency to wag and sway in turbulent air, occasionally causing a different kind of motion sickness. To make night flights more tolerable, many airlines configured their Constellations with heavy sleeper berths that folded down from the ceiling, allowing wealthy business travelers to actually lie completely flat under heavy blankets during transcontinental and transatlantic crossings. Yet this opulent use of cabin floor space severely restricted the total passenger capacity, driving up the cost of each individual seat mile and forcing the airlines to charge astronomical fares just to break even on the fuel and maintenance costs. It was an era of aviation where the sheer cost of operation naturally restricted air travel to the economic elite, and the airlines constantly battled to balance the weight of premium cabin amenities against the heavy payload constraints of the airframe. As the airline industry expanded rapidly throughout the late 1940s and into the 1950s, the demand for increased passenger capacity and longer ranges forced Lockheed into a relentless cycle of modernizing and stretching the original design. The result was the Lockheed L-1049 Super Constellation, an aircraft that saw the elegant fuselage stretched by over 18 feet, allowing airlines to cram significantly more paying passengers into the cabin to improve their razor-thin profit margins. To haul this longer, heavier airframe, Lockheed and Wright Aeronautical were forced to extract even more power from the aging engine architecture, leading to the development of the highly controversial turbo-compound engine variant. This deeply complex engineering solution involved attaching 3 blowdown turbines directly to the engine exhaust pipes, capturing the wasted kinetic energy of the hot exhaust gases and mechanically gearing that recovered power directly back into the engine crankshaft. This power recovery system miraculously boosted the engine output to an astonishing 3,400 horsepower and improved fuel efficiency by nearly 20%, allowing airlines to routinely fly across the Atlantic without stopping for fuel in Newfoundland or Iceland. However, the addition of the power recovery turbines introduced a staggering new layer of mechanical fragility to an engine that was already notorious for its temperamental nature and propensity for violent failure. The turbines operated in an environment of unimaginable heat and pressure, spinning at thousands of revolutions per minute, while being constantly bombarded by the highly corrosive, lead-rich exhaust gases expelling from the engine cylinders. The mechanical gearing connecting these blazing hot turbines to the main crankshaft was terrifyingly complex, and when a turbine bearing failed or a gear shattered, it frequently tore the rear section of the engine to absolute pieces, shutting down the entire power plant instantly. During night flights, passengers staring out the windows could clearly see a bright, terrifying stream of purple and blue fire constantly ejecting from the turbine exhaust ports, a normal operational characteristic that terrified nervous flyers and required flight attendants to constantly reassure them that the wing was not actually melting. The maintenance burden of these turbo-compound engines became so severe that flight crews routinely accepted that they would likely lose an engine during a long ocean crossing, placing immense pressure on the flight engineer to meticulously monitor oil temperatures and cylinder head pressures. The final absolute pinnacle of this piston engine lineage was the Lockheed L-1649 Starliner, a magnificent but tragically timed aircraft featuring a completely redesigned, massive straight wing that held enough fuel to fly non-stop from California to Europe. This supreme iteration finally achieved the ultimate payload and range goals that Howard Hughes had originally dreamed of, but it entered commercial service at a time when the entire paradigm of global travel was about to be violently and irreversibly overturned. Just as the complex, maintenance-heavy Starliner was taking to the skies, Boeing introduced the Boeing 707, a sleek swept-wing jet airliner powered by immensely reliable turbojet engines that possessed only a fraction the moving parts found in a radial engine. The jets flew twice as fast, twice as high, and most importantly, they offered a vibration-free, whisper-quiet cabin environment that made the pounding, rattling, oil-leaking piston airliners feel instantly antiquated and entirely obsolete. The paying public, having tasted the smooth, rapid flight of the new jet age, outright refused to buy tickets on piston airliners if a jet alternative was available on the same route, causing passenger loads on the Constellations to absolutely plummet overnight. The economic collapse of the large piston airliner market was devastatingly swift, and airlines that had just spent millions of dollars acquiring brand new super Constellations suddenly found themselves desperate to offload these massive, expensive assets. Almost overnight, the most beautiful airliners ever built were unceremoniously ripped out of prestigious, glamorous transcontinental passenger service and violently downgraded to hauling freight, agricultural equipment, and cheap charter flights on secondary unprofitable routes. The luxurious sleeper berths and plush lounge seating were ripped out and replaced with heavy aluminum cargo rollers, while the delicate interiors were permanently scarred by the rough loading of wooden crates and heavy machinery. Even in the cargo roll, the staggering fuel consumption and relentless maintenance demands of the turbo-compound engines proved too expensive for many operators, leading to vast fleets of these iconic aircraft being towed out into desert boneyards to be scrapped for raw aluminum. The entire global airline industry eagerly and rapidly transitioned to the pure jet economics of the Boeing 707 and the Douglas DC-8, leaving the complex oil-burning giants of the piston era to simply fade into obscurity. Yet, despite its ultimate commercial failure in the face of the jet age, the Lockheed Constellation remains historically significant for fundamentally altering the expectations of commercial air travel, dragging the industry out of the low-altitude doldrums into the pressurized stratosphere. It forced competing manufacturers to rapidly accelerate their own technological developments, pushing the boundaries of aerodynamics, hydraulic systems, and cabin pressurization, simply to keep pace with Lockheed's ambitious engineering gambles. The pilots who wrestled with its heavy controls and the flight engineers who fought a daily war against engine fires remember it as a deeply demanding machine that required absolute professionalism, commanding respect through its sheer complexity and unforgiving nature. It was an aircraft that visually embodied the post-war optimism and the romantic allure of global exploration, serving as a transitional bridge between the rugged, slow pre-war transports and the highly automated jetliners we take entirely for granted today. If you found this analysis useful, a like helps more people discover these deep dives. Thanks for watching.